Hello everyone! This is the second full video of the lecture course in organic chemistry dedicated to undergraduate students. Today we will speak about chemical bonds. It's one of the most important topics in the course because it's a basement of any chemical knowledge. We can treat chemistry as a science about breaking and formation of chemical bonds. Knowing the nature of chemical bonds, we can even predict some chemical properties of the substances we have never seen before. This is the following plan for today. First, we'll discuss the definition and origin of any chemical bond. Then, we'll show how the energy of a system changes if a bond is formed and explain it from the quantum mechanical point of view. After that, we'll discuss classification of chemical bonds and briefly describe ionic, covalent, and metallic bonds. Then, we'll thoroughly discuss the use of Lewis structures and the Octet Rule. After that, we'll learn a bit more information about the covalent bonds parameters such as length, strength, and polarity. For this purpose, we will introduce several definitions of atomic radius. Lastly, we will clarify why some compounds are polar and others are not. It means we will speak about the dipole moment of a molecule. Let's go! Bonding theories explain why some combinations of atoms are stable and others are not. For example, bonding theories explain why water's formula is H2O and not H3O. Bonding theories also predict the shapes of molecules, which in turn determine many of the physical and chemical properties of compounds. Scientists use knowledge about chemical bond formation to predict new drugs and new functional materials. I have two fascinating examples for you. Here, you can see the molecular structure of the protein, which makes cancer cells grow fast. Using our knowledge about how bonds are formed, to be more specific, intermolecular bonds in this case, scientists predicted the structure of the small molecule which is able to prevent the growth of cancer cells. It already has begun to save lives. By the way, there are two general types of bonds, the intramolecular and intermolecular one. The first one exists with one molecule between the constituent atoms. In contrast, the intramolecular bonds exist between two different molecules and are always much weaker than intramolecular bonds. On the slide you can clearly see some examples of different bonds. The intramolecular bonds are colored black, whereas intermolecular bonds are depicted in pink. And this pretty molecule is a part of new OLED displays. It's challenging to find which molecule would fit this technology, and there are lots of problems to solve and lots to improve regarding the efficiency of OLED devices. The knowledge about intramolecular chemical bonds and how they change upon absorption of light helps scientists to make our life brighter. There are many other nice examples in the different fields of chemistry, where the knowledge about chemical bonds' nature can help scientists to develop new technologies, for instance, increasing sustainability, new invisible materials, new extremely hard materials, and so on. So, I hope you're motivated enough for now and we can start talking about the chemical bonds themselves. What is a chemical bond? There are a lot of definitions of it, because it's a very broad concept. So, I have chosen one of the definitions. Chemical bond is a strong force of attraction holding atoms together in a molecule or crystal, resulting from the sharing or transfer of electrons. Atoms form a compound because as the atoms approach each other, the total energy of the system decreases, and this behavior is consistent with the principle of minimum energy. When we say there is a bond between two atoms in the compound, we mean that somehow interaction between these atoms makes the total energy of the system lower. But why, would you ask? How can we explain this phenomena? As you can see on the slide, there are attractive forces and repulsive ones. Attractive forces lead to decrease of the total energy of the system if atoms come closer to each other. In contrast, the repulsive forces lead to an increase of the total energy of the system while atoms are approaching each other. Let's briefly discuss the most important forces. The simplest attractive force is Coulomb attraction between positively charged nuclei and negatively charged electrons. The arrows on the picture show that a nucleus of one atom attracts the electrons of another atom. Here is the Coulomb law, which describes the interactions of charges, or in our case, charged particles. I recommend you to pause the video and calculate the energy of attraction between two charges, +1 and -1, at different distances, let's say 3 angstrom and 5 angstrom. Done? Here's the calculation example. I hope that it's quite obvious that energy at 5 angstrom is higher and thus less favorable than at 3 angstrom. On the other hand, the situation is completely opposite if we consider the Coulomb interactions between particles with the same charge. For instance, the electron-electron interaction and nucleus-nucleus ones. The arrows on the picture show that the nucleus of one atom is repelled by the nucleus of another, and also electrons of one atom are repelled by electrons of another atom. So these interactions are classified as repulsive, because the higher is the distance between particles, the lower is the corresponding energy. So let's illustrate how all discussed forces determine the energy of a system using a simple example, namely a diatomic molecule. Let's say we have just 2 atoms. Here you can see the dependence of the total energy of the system consisting of only 2 atoms, A and B, on the distance r between them. If the distance is r0, the energy is the lowest, so we have an energy minimum. It means that the difference between attractive and repulsive forces is the biggest. So the chemical bond is formed and the bond length is r0. If we increase the distance, the energy starts to grow, as the Coulomb attraction between electrons and nuclei corresponding to different atoms becomes weaker, and at some point, the distance is so long that we can say that there is no bond anymore. Furthermore, if we try to make distance smaller than r0, the energy also increases. The reason is that repulsive forces start to dominate in this case. That's why atoms do not have infinitely small bond length. Sometimes attractive forces are too small, while repulsive are too big, and there is no bound state. In this case, the chemical bond is not formed at all. Until now, we have tried to describe the chemical bond using only laws of classical physics. Unfortunately, classical physics cannot treat the movement of very tiny particles in an adequate manner. For this purpose, we should use quantum mechanics. It's a very broad branch of physics, which helps us to describe the behavior of very small particles, such as electrons, for example. These particles are so small that we don't even know if it's a particle or a wave. It is something in between. Well, I guess it's quite obvious now that any chemical bond should be described with electron-electron, nuclei-nuclei, and electron-nuclei interactions. All these particles are very small and behave according to the laws of the quantum world, not the classical one. Now, on the slide, you can see the Schroedinger Equation. It's one of the central equations in quantum physics. Let's briefly describe what all these letters stay for. H stands for molecular Hamiltonian operator. It corresponds to the total energy of a system, including both kinetic and potential energy. Psi is called wave function of a system, and it's connected to the distribution of electrons and nuclei in space. And E is the energy of the system. Of course, to explicitly define H, we should write the sum of all the Coulomb interactions and kinetic energy terms for electrons and nuclei. As a result, we will obtain this huge equation, which is impossible to solve for most systems of interest. However, using some approximations, we're eventually able to get the result, namely the dependence of the energy on the coordinates of all atoms. Thus, we can describe which bonds do form and which do not, as we did it for a diatomic molecule. We aren't going to dive deeper into quantum mechanics and quantum chemistry to solve it explicitly, because it's an organic chemistry course and not a theoretical one. However, we will get introduced to approximations that people use while discussing different theories of chemical bonding. Bonding theories help us to predict the circumstances under which bonds form and also the properties of the resulting molecules. So, for now we understand well what a chemical bond is and what are the driving forces of its formation. That's the right moment to classify types of bonds. We can roughly classify chemical bonds into 3 types depending on the kind of participating atoms. The first type usually exists between metals and non-metals. It is called ionic bond. From the school classes you already know that metals tend to have low ionization energies, that is, their electrons are relatively easy to remove, and that non-metals tend to have negative electron affinities, meaning that they readily gain electrons. When a metal atom bonds with a non-metal atom, it transfers one or more electrons to the non-metal. The metal atom becomes a cation and the non-metal atom an anion. These oppositely charged ions attract one another, lowering their overall potential energy as described by Coulomb's law. The resulting bond is ionic. The next popular bond is called covalent bond. Nonmetals tend to have high ionization energies, which means that their electrons are relatively difficult to remove. Therefore, when a nonmetal bonds with another nonmetal, neither atom transfers electrons to the other. Instead, the two atoms share some electrons. The shared electrons interact with the nuclei of both of the bonding atoms, lowering their potential energy following Coulomb's law. The resulting bond is a covalent bond. The third type of bonding, namely metallic bonding, exists in metals. Since metals have low ionization energies, they tend to lose electrons easily. In the simplest model for metallic bonding, called the electron C model, all of the atoms in a metal lattice give up their valence electrons. These electrons are no longer localized on a single atom, but delocalized over the entire metal. The positively charged metal atoms are then attracted to the sea of electrons holding the metal together. The last column in this chart shows us that some weaker chemical bonds can occur between molecules and not inside them. As you remember, we have discussed these bonds briefly today. The most important for us will be the hydrogen bond. A hydrogen bond is a primarily electrostatic force of attraction between a hydrogen atom, which is covalently bound to a more electronegative atom or group, and another electronegative atom, having a lone pair of electrons, the hydrogen bond acceptor. The most frequent donor and acceptor atoms are the second row elements such as nitrogen, oxygen, and fluorine. Hydrogen bonds can be intermolecular or intramolecular. Once again, intramolecular means that these bonds occur among parts of the same big molecules such as DNA or proteins. You can see both variants of hydrogen bonds on the slide right now. Here you can see once again a table summarizing all essential information about various types of chemical bonds that we mentioned. Don't hesitate to pause the video and inspect the table carefully. We have seen earlier that there are three major types of bonds: covalent, ionic, and metallic. The covalent bonds lie at the heart of organic chemistry, and there's quite much to understand about them for every organic chemist. As we have previously discussed, the covalent bond is such a bond that is typically formed between two nonmetals. To be more specific, two electrons are usually shared between the nuclei of atoms involved in the bonds. Of course, in order to speak about anything, we need a certain way of graphical representation of it. The same is true for covalent bonds. We need some way to represent these bonds on paper or slide. That's why chemists have developed multiple ways of depicting covalent bonds, and one of the most popular representations is called the Lewis structure. Several examples of Lewis structures can be seen on the screen now. Before discussing it in detail, it is reasonable to refresh some basic knowledge about the atomic structure. As you know, the electrons in an atom can be divided into two subgroups: the core electrons and valence electrons. The core electrons are located closer to the nucleus and thus are held quite strongly. In contrast, the valence electrons are located much farther from the nucleus and, according to previously discussed Coulomb's law, are held most loosely. Here is Coulomb's law once again. That's why the core electrons do not participate in the formation of any chemical bonds, whereas the valence electrons are responsible for bond formation. In other words, the valence electrons define the chemical properties of elements. The Lewis structures of compounds and Lewis symbols of elements reflect only the number of valence electrons, while the core electrons are omitted for clarity. Well, it's enough theory, let's run to the practice. On the slide you can see a general structure of a Lewis symbol. It is very simple. In a Lewis symbol we represent the valence electrons of main group elements as dots surrounding the element symbol. Here you can see the electron configuration of nitrogen. We won't discuss it in detail because we hope you remember such basic material from the high school or inorganic chemistry course. It is obvious that nitrogen has 5 valence electrons, and it's very simple to deduce the Lewis symbol for it. Just count the number of electrons and draw them as dots surrounding the capital N, as shown on the screen right now. Despite it being very simple material, I would ask you to pause the video and try to write the Lewis symbol of sulfur. Done? Here's the right answer, check yourself. I'm pretty confident that you have managed to do it, and we can move on. Now we know how to draw the Lewis symbol for any atom. From the inorganic chemistry course, we know that many elements tend to form chemical bonds, and thus build a compound. But I guess you have heard about the noble gases that either don't form any compounds or do it not so willingly as other elements. Now on the slide you can see several compounds formed by noble gases. I hope you like their structures. The reason for such a behavior is the full outer electron shell of a noble gas. Apart from helium, all of them have 8 electrons on the outer electron shell. You can see their electron configurations on the slide right now. You might remember that this electron configuration is very stable, and that's why all other nonmetals tend to share their electrons with other elements, thus gaining 8 electrons in total. And this leads us to the well-known Octet Rule. The Octet Rule postulates that the main group elements tend to bond in such a way that each atom has 8 electrons in its valence shell, giving it the same electronic configuration as a noble gas. To be more precise, a closed shell with an ns2-np6 electron configuration in which n is the energy level number. Okay, now we understand why atoms form covalent bonds. It's the proper time to speak about the Lewis structures. A Lewis structure is a very simplified representation of the valence shell electrons in a molecule. It is used to show how the electrons are arranged around individual atoms in a molecule. Like in the Lewis symbols, the electrons are shown as dots. While drawing the correct Lewis structure of a compound, the goal is to obtain the best electron configuration. It means that the Octet Rule is followed and also the formal charges need to be satisfied. It is reasonable to look at the Octet Rule first and then move to the formal charges. Let's try to describe some well-known molecules using Lewis symbols. The first molecule we describe will be HBr. On the right hand side you can see the electron configurations of hydrogen and bromine atoms. So the corresponding Lewis symbols are quite obvious. Hydrogen has only 1 electron highlighted in pink, and bromine has 7 valence electrons in blue. In the bottom left corner you can see the 2 Lewis structures of the HBr molecule. Both of them are equivalently correct. Pay attention that we have an octet of electrons around the bromine atom. In contrast, a hydrogen atom has only 2 electrons that form the actual covalent bond. Hydrogen doesn't follow the Octet Rule, remember it. For the sake of simplicity, we can draw a solid line instead of 2 shared electrons. Now you understand the origin of solid lines that represent covalent bonds and structural and skeletal formulas that we have discussed previously. Well, now it's your turn. Pause the video and try to draw the Lewis structure of the O2 molecule. Done? Let's check together your solution. The electron configuration of the oxygen atom is shown now on your screen. The corresponding Lewis symbol is given on the left-hand side of the slide. Finally, the Lewis structure of O2 is given now at the bottom. Pay attention that we have an octet of electrons around each of the oxygen atoms. 2 electron pairs are common, which means that we have a double bond. Let's substitute the corresponding pair with 2 solid lines that stay for a double bond. I hope that everything is clear now. If not, you know where the comments are, and don't forget about the webinars that we organize based on the questions that you leave in the specific threads on our forum. All links are in the description below as usual. Okay, we have formulated the Lewis structures for diatomic molecules. Of course, our next goal is the Lewis structure for a polyatomic molecule. Let's begin with PCl3. Its 3D model can be seen on the screen now. Isn't it beautiful? As usual, we begin with the electron configurations of the constituent atoms. They can be seen on the right-hand side of the slide. Then we move on to the Lewis symbols of phosphorus and chlorine. They can be seen on the left-hand side. Phosphorus has 5 electrons, 3 of them are unpaired, whereas chlorine has 7 in total and only 1 is unpaired. It means that phosphorus can form 3 bonds and each chlorine can have only 1. The corresponding Lewis structures are located as usual at the bottom. Pay attention that we have an octet of electrons around all atoms and some lone pairs. This time I have circled all electron octets with corresponding colors so that you can see exactly how we count electrons. The last thing that we need to do is to substitute shared pairs with solid lines. Now, let's try to apply the Lewis scheme to the polyatomic molecule with a double bond, for example, ethylene. As you might remember from our previous lecture, ethylene corresponds to the class of hydrocarbons called alkenes, and here you can see its 3D structure. In the subsequent videos we will explain why it's planar, so stay tuned. It consists entirely of carbons and hydrogens, and no heteroatoms are present. Now the electron configuration of carbon and hydrogen atoms are shown on the screen. If the carbon atom is in the excited state, we can get this electron configuration, where the carbon atom has 4 unpaired electrons. They are highlighted in blue in Lewis symbol and electron configuration. So the Lewis symbols of these atoms are quite trivial and are shown on the left hand side right now. Finally, we get our Lewis structure of ethylene, which is located at the bottom. It is obvious that both carbons are surrounded by 8 electrons each in total, meaning that the octet rule is followed properly. The highlights should help you to follow the electron counting. If it's not obvious, pause the video and take your time. I have also mentioned that the formal charges shouldn't be taken into account. But what is the formal charge? Actually, it's very simple. The formal charge is the difference between the number of valence electrons of an atom in a neutral free state and the number assigned to that atom in a Lewis structure. Let me show it to you based on 2 examples. Here's the Lewis structure of carbon dioxide. On the left, you can see the Lewis symbols of carbon and oxygen. Carbon has 4 valence electrons, while oxygen has 6 of them. I have colored the electrons attributed to oxygens in red and to carbon in blue. As you can see, carbon still has 4 and each oxygen still has 6 electrons. If we subtract the number of electrons that carbon has in the Lewis structure and in the free state, we will obtain 0. It means that neither carbon nor oxygen has formal charges. Pause the video and inspect the calculation by yourself carefully once again. Remember that the way you count the electrons for the octet rule and formal charges are different. While considering the formal charges, we count only 1 electron from each shared pair that represents a bond. Well, here's the Lewis structure of the acetate anion. You can clearly see that oxygen is surrounded by 3 electron pairs and forms 1 carbon-oxygen bond. It still has an octet, but the formal charge in this case equals -1. Once again, don't hesitate to pause the video and inspect the calculation carefully. The general rule that you should remember from the inorganic chemistry course is that you should try to formulate such a Lewis structure in which all atoms have an octet rule and the number of non-zero formal charges is the smallest possible. And another important fact about the formal charges. The formal charges should match the electronegativity of the atom. That is, negative charges should be on the more electronegative atoms and positive charges on the least electronegative atoms if it is possible. For example, we should place a formal charge of -1 on oxygen instead of carbon, and +1 on carbon is much better than on oxygen. Here are a few examples. Take your time to inspect them and ask your questions below if anything remains unclear for you. I should also stress the fact that formal charges don't reflect the real charge distribution in a molecule, it's just our model that exists for convenience. Lastly, if we sum up all the formal charges within a molecule, we obtain the real charge of our ion or molecule. Here is the already discussed example of acetate anion. At the bottom you can clearly see how to calculate the real charge of a molecule using the formal charges in Lewis structures. And pay again your attention to the location of the negative charge. It strictly correlates with the electronegativity of the atoms, just as we discussed before. As you have already seen, nothing is perfect, even the octet rule. The octet rule is not valid for hydrogen and helium because there is no 1p level. So for these atoms works 2 electron rule, as you saw in the example with the HBr molecule. It means that hydrogen can have only 1 covalent bond, as it tries to gain 2 electrons in total, just as helium has. Also, the elements in the 3rd row and beyond that, which have d electron level, tend to make hypervalent molecules such as ICl5. Hypervalent compound is a molecule that contains 1 or more main group elements, apparently bearing more than 8 electrons in their valence shells. Phosphorus pentachloride PCl5, sulfur hexafluoride SF6, chlorine trifluoride ClF3 are examples of hypervalent molecules. Their formulas, 3D models, and Lewis structures can be seen on the screen now. There are different opinions regarding the Lewis representation of hypervalent compounds. Some researchers say that it is essential to draw an octet for any atom that is hypervalent. Others tend to be not so strict and allow to draw more than 4 bonds for such atoms as sulfur, phosphorus, chlorine, etc. In our opinion, it doesn't really matter because it's just our formal way of representation. Moreover, it's just a model that has a quite lot of approximations. Nevertheless, let's take a look at the loose structure of the hypervalent molecule ICl5. The electron configurations of iodine and chlorine atoms are shown on the right. If iodine is in the excited state, we can get such an electron configuration where the iodine atom has 5 unpaired electrons. So the Lewis symbols of these atoms are shown on the left-hand side of the slide. Red dots in the Lewis structure of iodine represent unpaired electrons. Finally, the resulting Lewis structures of the ICl5 molecule are given at the bottom. Pay attention that we have more than 8 electrons around iodine and octet around chlorine. Of course, we can redraw this Lewis structure by adding formal charges in such a way that iodine and all other constituent atoms have an octet of electrons. As this video is dedicated to the fundamentals of organic chemistry, we will not discuss further the Lewis structures. Of course, there is much more to deal with, for instance 2-electron 3-center bonds, but you will learn it in the inorganic chemistry course. This was just a brief recap of the necessary material that you should have learned during your high school chemistry classes. So let's move on and discuss the energy of covalent bonds. Earlier today we saw how the energy of the system that consists of 2 atoms depends on the distance between them. Just take a look at it once again. When the atoms approach each other, the energy of the system decreases because atoms share their electrons, thus forming a covalent bond. This energy is released, for example, in the form of heat. If we try to separate atoms from each other, then the energy of the system begins to increase, and it means that we need to supply energy to the system to break a chemical bond. The covalent bond can be treated as broken when the energy of a system doesn't change significantly upon bond elongations. We have just highlighted this situation on the graph. It is also important to note what happens with the shared electron pair during bond cleavage. Obviously, there are 2 possibilities. Electrons can be distributed equally between 2 atoms, just as shown on the left-hand side. In this case, we name the process of bond cleavage as homolytic cleavage, and it leads to the formation of 2 neutral particles, in this case, atoms A and B. In contrast, if both electrons after cleavage are attributed to one atom and the other has gained no electrons from the shared electron pair, then we call this cleavage to be heterolytic. In this case, anion and cation are formed. I should stress out the fact that homolytic cleavage is much more preferable in a gaseous state than a heterolytic one, while in liquid media it's quite complicated to predict the more favorable pathway. I guess now it's time to define the concept of covalent bond strength. We measure the strength of a covalent bond by the energy required to break it. That's the energy necessary to separate the bonded atoms, just as I showed you using the graph with atoms A and B. The stronger the bond is, the greater the energy required to break it is. The energy required to break a specific covalent bond in 1 mole of molecules in gaseous state is called the bond energy or the bond dissociation energy. It is also important to note that in this case we're talking about the homolytic bond cleavage. Remember this definition, because we will use it quite often when dealing with alkanes and their chemical properties. Lastly, let's look at some important bonds in organic chemistry and their energies. The energy of a typical CC single bond is 345 kJ per mole. The energies of double and triple CC bonds are much higher, namely 611 and 837 kJ per mole respectively. It means that every additional pair of shared electrons makes the overall attraction stronger and thus harder to break. While dealing with alkenes and alkynes in greater detail, you will see that bond energies correlate also with the bond length. Well done! I hope everything is clear for you now, and we can move on to the next topic for today. We remember the basic atomic structure. To be more specific, the atomic nucleus consists of protons and neutrons, while electrons form the so-called electron density that surrounds the nucleus. On the slide, you can see that electrons are located on the orbitals, and it may seem that the distance between an electron and nucleus remains constant and is well defined. However, it is not true. The picture on the slide is just a model. In reality, we cannot know the exact position of an electron. It means that we know only some region in space around the nucleus, and we can predict the probability to find an electron in this region. I hope it is quite obvious from the figure on the slide that the more dots we see in some region, the higher is the probability of finding it there. And of course, the farther from the nucleus, the less is the probability to find an electron there. Undoubtedly, it is a very simplified description, but it is sufficient for us now. Such behavior is the result of the quantum mechanical nature of an electron. If an electron movement could be correctly described with classical mechanics, then the representation on the slide was a good model, and based on it, we could have predicted the radius of an atom as the distance between the farthest electron and atomic nucleus, just as it is shown on the slide right now. In reality, the situation is much more complex, so we need to develop some more sophisticated methods to define the atomic radius. Scientists have created several widely applicable models for this purpose, so let's discuss them one by one. The first definition of the atomic radius applies only to the simplest chemical structures, namely atoms or ions with only one electron. This radius is called the Bohr radius. It is named after a brilliant physicist Niels Bohr, who published an article about the atomic structure back in 1913. In this paper, he has proposed several ideas that lie at the heart of Bohr's atomic model. If you are interested in reading this fundamental paper, check the specific thread on our forum. It is uploaded there as a PDF. And no worries, the math that is used there is more than trivial. The Bohr radius, symbolized A, is the mean radius of the orbit of an electron around the nucleus of a hydrogen atom at its ground state. It is a very important physical constant, and its value can be seen on the screen right now. Unfortunately, in chemistry, we don't use it anymore for the determining of atomic radius. As I have mentioned before, the main limitation is that this radius is valid only for one electron systems, whereas the organic molecules contain hundreds of them. Let's move on to the more useful definitions. The second definition is named after another renowned physicist, Johannes Diederik van der Waals. You probably have already heard about the van der Waals forces and van der Waals equation of state during inorganic chemistry lectures. The definition of atomic van der Waals radius is fairly simple. The van der Waals radius of an atom X is half of the distance of the closest approach of two non-bonded atoms of X. So let's illustrate this concept using the following example. Now on the slide you can see two S8 molecules and their 3D model that somehow resembles a crown. At room temperature, these molecules form a solid substance. Here is the corresponding crystal structure. However, we can easily evaporate it, obtaining the gas phase. The S8 molecules move rapidly in gas and repel each other due to electrostatic forces between their electron shells. The half of the distance of the closest approach of two S atoms that belong to the different molecules is their van der Waals radius. On the slide it is colored red and denoted as RV. There are various experimental and theoretical techniques to determine or measure the van der Waals radius of an atom, but we will not discuss them today. You just need to understand the definition and remember that both atoms are not covalently bound to each other. It means that they don't share electrons at all. Well done! The last atomic radius definition for today is the covalent radius. To define the covalent radius of an atom, we need to define the covalent bond length first. The covalent bond length between atoms A and B is equal to the distance between their nuclei. Yeah, it's that simple. Now on the slide you can see several organic molecules and some of the covalent bond length that are predicted with quantum chemical calculations. The typical units for bond length are angstrom, which equals to 10 to the power of minus 10 meters, and picometer, which is 100 times smaller and corresponds to 10 to the power of minus 12 meters. Pause the video and inspect the given bond length. Now we have enough knowledge to define the covalent atomic radius. It is just half of the internuclear separation in a homonuclear XX single bond. Here on the slide you can see the halogen molecules, their covalent bond length and covalent atomic radii. I would also like to mention that the covalent atomic radius is also smaller than the corresponding van der Waals radius. Here on the slide you can see two tables. The first one represents the covalent atomic radii, and the second one provides the van der Waals radii for the same atoms. Well, I guess these tables perfectly illustrate my last statement about the relations between these two types of atomic radii. We have covered pretty much of the new information for today. I hope everything is clear for you now, and if not, you know where the comments are, and don't forget about the webinars. You're welcome to ask all the questions in the specific threads on our forum. One limitation of representing electrons as dots and covalent bonds as two dots shared between two atoms is that the shared electrons always appear to be equally shared, But it's not always like this. Let's move on to the next to last topic for today. Take a look at the Lewis structure of the HBr molecule that we discussed earlier today. I hope you remember from your high school chemistry classes that bromine is more electronegative than hydrogen. For those of you who don't remember, here is a brief recall. Electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. There are several ways of calculating the electronegativity of an atom, and the most popular one is the Pauling scale presented on the slide. The higher number is, the stronger an atom pulls the shared electron pair. It is obvious that bromine pulls the electrons to itself much stronger than hydrogen due to higher electronegativity. It means that the electron pair, of being more precise the electron density, is not equally distributed between hydrogen and bromine. It is concentrated more on the bromine atom. But the Lewis structures don't give any clue about this unequal distribution. By the way, chemists and physicists call this phenomena polarization. Now we need to recall in our own memory a very important fact: the electrons are negatively charged. And if there is a much higher probability to find them in the proximity to bromine, it is partially negatively charged. On the other hand, the hydrogen atom should have a positive partial charge of the same magnitude, because the overall charge of the molecule is zero. It means that if we sum up all partial charges of the atoms in a neutral molecule, we should obtain zero. Sometimes we are not really interested in the magnitude of partial charge. Instead, we just want to indicate that the electron density distribution is not equal. In this case, we just use these deltas with corresponding signs as shown on the right hand side now. Another way to show the polarity of the bond is to use arrows as shown on the left hand side. So let's illustrate the concept of bond polarity using the previously discussed molecules. Here's an oxygen molecule O2. It consists of the same atoms with equal electronegativity. So the electrons are pulled with equal strength, thus the bond is nonpolar, meaning that electrons are equally distributed between atoms. And here's the phosphorus chloride, PCl3, from our previous video. P is less electronegative than chlorine, meaning that electrons are pulled stronger by chlorine. It leads to the unequal distribution of the electron density, so there is a more negative charge on chlorine atoms and a more positive charge is located on phosphorus. That's why we can name the PCl bond polar, and we can indicate it by using arrows or deltas as shown on the slide. Just a rule of thumb is that the greater the electronegativity difference between the atoms, the more polar the covalent bond between them is. Well done! Now we know how to determine if a bond is polar or nonpolar and the ways to graphically depict it. As usual, here's the exercise for you to solve. Determine if the bonds are polar or nonpolar. If the bond is polar, then attribute the partial charges using deltas or arrows. Pause the video and solve it. Here are the right answers. Check yourself. If you have any questions or mistakes, feel free to ask your questions in the corresponding threads on our forum. Most of the questions will be discussed during the webinars. The last topic we'll discuss today is the dipole moment. This property defines if the whole compound is polar or nonpolar based on the information about its structure and bond types. The dipole moment is important for organic chemists because using it we can determine which solvents our compound is soluble. It is reasonable to begin with the standard definition from physics. The electric dipole moment is a measure of the separation of positive and negative electrical charges within a system, that is a measure of the system's overall polarity. In other words, when two electrical charges of opposite sign are separated by a distance, an electric dipole is established. As we have already seen, the electrons aren't distributed equally within a molecule due to differences in the electronegativity of the constituent atoms. It means that a diatomic molecule can form a dipole and should be treated as an electric dipole. The dipole moment of a diatomic molecule is given by the equation on the slide right now. Here the letter d is the distance between point charges, and for chemists, it is just the internuclear distance or covalent bond length. E is the charge of one electron, and its value can be seen on the screen now. Lastly, the letter q is the magnitude of the point charge. The dipole moment itself is denoted with the Greek letter mu. The SI unit of mu is the coulomb meter, but for convenience, mu is usually given in units of dBi. As I have already mentioned, The points charges on atoms denoted with the letter Q arise from bond polarity, and they are equal to magnitude of the partial atomic charges that we have just discussed. For a better understanding of this concept, let's solve together a problem given on the slide. The bond length in HF is 92 pm and the dipole moment is 183 dBi. Determine the partial atomic charges in the molecule. First, let's rewrite the dipole moment formula with the respect to the point charge Q. Q equals the dipole moment divided by electron charge and the internuclear distance. Now we can calculate the charge distribution by substituting variables with the previously given data. Well done! Here you can see the calculated value of Q. It means that we can attribute the positive partial charge of magnitude Q to hydrogen and the negative partial charge of magnitude Q to fluorine. Pay attention that the molecule itself is not charged, meaning that the overall charge is zero. But the world would be much simpler if all quantities were scalar. Unfortunately, it's not, and the dipole moment is a vector quantity, meaning that it has a direction in space. And what do we use to show direction? Hell yeah, vectors. So the dipole moment of a polyatomic molecule is a vector, and it can be calculated with the formula represented on the screen. Here the Qi is the magnitude of the ith charge, and Ri is the vector representing the position of the ith charge. Of course, we can assume that the charges have the same coordinates as the atomic nuclei, meaning by iterating over I, you iterate over atoms. Okay, first we need to define the origin of the coordinate system. The theory states that if the molecule is neutral, then the choice of the center does not influence the resulting dipole moment. Second, we should determine the coordinates of all atoms in our molecule and represent them in a vector form as shown on the screen now. I recommend you to pause the video and inspect the slide carefully. Take your time and make your notes. It should enhance your memorizing significantly. Lastly, we need to use the Q values and use the initially given formula for a dipole moment of a polyatomic molecule. Let us calculate the dipole moment of water, knowing all the data about geometry and charges. First, locate the center of the coordinate system on the oxygen atom. Then the R3 vector is 0. Then we determine the vectors for both hydrogen atoms. The results are also given on the slide. Pay attention to the fact that vectors R1 and R2 point from hydrogens to oxygen. This is a general rule that the vectors should point towards the more electronegative element that bears partial negative charge, in this case, the oxygen atom depicted in pink. Then let's multiply the vectors R1 and R2 by the corresponding charges denoted with Q. The last step is the summation of vectors R1 and R2, followed by finding the length of the resulting vector. The length of a resulting vector is 1.2 angstrom, and the direction is shown in the figure with the blue vector. This is the direction of the overall dipole moment of the water molecule. Lastly, to calculate the dipole moment of the water molecule, we need to multiply the vector length by charge separation 0.33, then by elementary charge E depicted in green, and then convert the obtained value in dBi as shown in figure in violet. Okay, the calculated dipole moment of water is 191 dBi, which is very close to the experimentally determined value of 1.87 dBi. From the answer we can deduce that water is a polar molecule, and it can be used to dissolve other polar substances. If the dipole moment is 0, then the molecule is said to be nonpolar. Pause the video and try to choose nonpolar molecules based only on their geometries and constituent atoms. Done? Here are the right answers. As you can see, both CCl4 and CS2 molecules are nonpolar despite the polar covalent bonds present in them. The reason is the vector nature of a dipole moment. In these molecules, the vectors that describe CCl and CS polar bonds point in different directions but have equal magnitudes as shown on the slide. That's why their summation leads to zero overall dipole moment. So these molecules are nonpolar, and they can be used as solvents for other nonpolar substances. Ultimately, the dipole moment depends on both on the electronegativity of the elements and on the geometry of the molecule. Well, that's it for today. Let's briefly revise what we have learned today. First, we discussed the definition and origin of any chemical bond. Then, we showed how the energy of a system changes if a bond is formed and explained it from the quantum mechanical point of view. After that, we discussed classification of chemical bonds and briefly described ionic, covalent and metallic bonds. Then we thoroughly discussed the use of Lewis structures and the Octet Rule followed by the exceptions from them. After that, we learned a bit more information about the covalent bond parameters such as length, strength, and polarity. For this purpose, we introduced several definitions of atomic radius. Lastly, we clarified why some compounds are polar and others are not, speaking about the overall dipole moment of a molecule and illustrating the theory with the worked examples. If you have any questions related to this video or any topic in chemistry, biochemistry, or pharmaceutical sciences, you are more than welcome to ask them on our website and forum or in the comments below this video. We'll be glad if you give us a like and subscribe to our channel. Thank you very much for your attention and we'll meet once again in the next video.